My name is David Tarkelson, a research scientist at the Agricultural Research Service in Twin Falls, Idaho. I'd like to recognize my co-authors and contributors to this particular data set, both from ARS as well as from Amalgamated Sugar Company. The purpose today is really to present some compelling evidence that a static range nitrogen management approach in Northwest U.S. sugar beet production could be valid. It needs to be assessed and looked at. As we go through the data today, just remember that we are not trying to recommend what that range is at this point in time. This is really just to show the concept and how the data backs up a potential concept of a static range nitrogen management approach. So when I say the Pacific Northwest sugar beet growing area, I'm really referring to this particular area here, mainly in southern Idaho and eastern Oregon, of about 182,000 acres of sugar beets planted and harvested annually. Of course, that number goes up and down, but that's kind of a good average. So within the world of soil fertility and nitrogen management, we're really trying to optimize crop yields and at the same time minimize losses. That really is the overall goal. So applying the right amount of nitrogen is really important. And so understanding all the inputs of nitrogen is extremely important. With sugar beets and most crops, the amount of nitrogen in the soil in the spring and the soil sample and fertilizer are extremely important to manage those two components together so that we get the right rate of nitrogen put on and minimize those losses. So in most of our crops, including sugar beets, we're trying to supply the required amount of nitrogen in the right amounts. We don't want to oversupply or undersupply. And so we're talking about ammonium and nitrate. Those are the two forms that are available. And to get this, we have three different suppliers. We have the residual soil nitrogen, which is taken with a soil sample in the spring at a snapshot in time. However, it does not account for all the nitrogen that's going to be made available through the growing season. The second component is the in-season mineralized N, which is that growing season availability of nitrogen. And this is the mineralization of organic nitrogen to produce ammonium and nitrate. This really is not understood very well. And this is not the time to get into that. I have another presentation in this conference that talks about this. But this really is a cloudy area that we can't reliably predict. So what we do is we understand what we have there first, the soil, and then we try to match the remainder of what our supply is with fertilizer. So as I go through this presentation, these are a couple of terms and definitions you're going to want to remember because we're going to refer back to them often, and I want you to make sure you understand that. So when I talk about nitrogen supply, we're referring to the supply of both nitrate nitrogen, in addition ammonium nitrogen, and that is both from the soil and the fertilizer. Okay, so it's a combination of those two different suppliers that we talked about in the previous slide. We're also going to refer to this idea of a nitrogen rate. This is the yield goal based approach or factor that's being used to help determine a nitrogen supply requirement for sugar beets. And so it's called a nitrogen requirement, the NR factor, and that is the pounds of nitrogen needed or needed to be supplied per ton of sugar beet roots. Okay, that's a common factor that's used in yield goal based approaches in our growing area. These NR factors are determined from research over time, and we're going to show that. We're going to show three different instances where nitrogen rate factors were determined based upon a set of research projects that were done to determine nitrogen management practices for sugar beets. And to get the required nitrogen supply, okay, and how much nitrogen we need to supply per pounds of nitrogen per acre, we just take the NR factor, which is in pounds of nitrogen per ton, we multiply that by a projected root yield. And that can be based upon historical data or any other average yields for a given year that you expect, a producer expects to get on his field. When those are multiplied by each other, that gives you the required nitrogen supply that's needed. And you can combine both the soil supply and the fertilizer supply to get to this required N supply. This slide shows the three different nitrogen requirement factors that were determined through research over time. The initial one in 1977 publication from studies that were done prior to that. The number of studies was not really known, but we do know that it was done, and a factor of 8 pounds of nitrogen per ton of beets was established at that particular time. About 20 years later, in 1997, a new requirement factor was determined at 7.3 pounds of nitrogen per ton, and that was a result of 18 study sites. In 2011, a summary of 14 study sites was evaluated and indicated that the nitrogen requirement factor needed to be lowered to 5.5. So the question is, why was the NR factors going down? Looking at that and doing some evaluation and putting some historical data together and doing an analysis, this idea of a static range approach started to come about. And so it was after this 2011 publication that we started doing this analysis, and the data indicated that a static range approach may be something we want to evaluate. And I'm going to present some of that information to you today. So also, besides presenting the data that I was just talking about to you, that indicates a static range approach may be appropriate, we decided, along with Amalgamated Sugar Company, to conduct more research to evaluate this concept of a static range approach. We looked at 6 more studies in 2018 and 2020 to evaluate this even further. And you can see some of the details of the study over on the right-hand side, as well as the locations of the studies across southern Idaho. I want to go through with you what we did earlier when we started to analyze data and look at these different data layers that led us to believe that perhaps a static range nitrogen management approach would be superior to a yield goal based approach. And that analysis was really looking at some different data layers, and these 3 data layers here really, when superimposed on top of each other, told a really intriguing story. So I'm going to bring each of these data layers up on top of each other sequentially to show you kind of a story and a progression in our logic string. So you can see that when you multiply as I said before, a yield by the yield goal nitrogen rate factor, requirement factor, what you end up with is with a needed nitrogen supply right here. Okay, so if you multiply 1 times 2, you get 3. And so we're going to bring that data up onto this graphic, and you're going to hopefully be able to see what we're talking about. The very first data layer here is yield. This is showing the average annual sugar beet yield across the entire growing area, not just Idaho. The graph is mislabeled. It's actually across the entire growing area over time. I have the standard units on this side, tons per acre, and the metric units will all be supplied on this side. So as I add these data layers, they're going to be superimposed on top of this graph with the same timeline. You'll have just a different y-axis with different units on there. But this is really going to help you give a really good graphical demonstration. The one thing about yields you want to notice is that there's a gradual increase early on up until about 2006, 2007. Then we started seeing this drastic increase in yields up to about 0.7 tons of sugar beets per year increase. And if we look at our formula down here with these 3 different layers, this is supplying you with the average annual yield. The next data layer I'm going to bring up to put on here is the NR factor. Okay, so now we have our NR factor, yield goal based NR factor placed on here from the research. So the important point is this is research based. These were determined by research. Okay, so these are actual values, not just estimated. And these are in pounds of nitrogen per ton on the standard side. If I go down here, you look at the what we're actually doing the calculations. So we have the yield. Now we have our NR factor placed on here. The one thing to notice, and I think the important thing to recognize on this particular graph, is these NR factors, which are based upon research located with these organizations doing the research, over time are going down. Right? We mentioned that before. At the same time, our root yields are going up. So what ends up happening when you multiply the average annual root yield or a projected root yield times the research-based nitrogen requirement is based upon a yield goal. You have two things happening. One's going down, one's going up. And what we're going to now plot on here is the needed N supply, which is basically the product of multiplying these two factors together at these different times. So on top of this graph, now I've now superimposed the N supply data layer. This is the nitrogen supply needed to maximize yield. I'm bring up my pointer again. There we go. So the nitrogen supply to maximize yields, particularly sucrose yields, are listed on this axis. And because these are a product of the NR, the nitrogen requirement yield goals base factor, and the yield, you can see that as one factor goes down, the other goes up. You end up having a very stable, static product across time. In this case, as we get this needed N supply, you can see that it's in a very narrow range over time, a range of about 6 pounds of nitrogen per acre. That's not a huge amount of difference from 1977 to 2011 in terms of how much nitrogen is needed to maximize sucrose yields. It's a very narrow range. And that it really was what got us thinking that, boy, when you look at this data this way, a static range approach really does make a lot of sense for our production systems. You can see here that the NR factor that we published in 2011 came from research conducted over 14 site years, as mentioned before. This data has been published in 2 different publications. It can be looked at right now. What I want to do now is I want to include the new data and see where it fits on this. So really the purpose of this new data set was really to continue to evaluate this particular concept. What is our NR factor going to be, and what is our maximum our nitrogen supply to maximize yield going to be compared to these past research studies? And this shows you what we found out, that the average nitrogen requirement value when calculated was about 4.3. Of course, there was a range of 3.2 to 5.4, but on average, that's what it was. And when you multiply this new NR factor from research by the average yields of today, this is the nitrogen supply needed to maximize yield that came out. Still within that narrow range. The absolute range, if we look at it, is about 13 pounds of nitrogen per acre difference across this entire period of time. So this particular graph, I want to show a scenario where what would happen to nitrogen supplies if we just relied upon these nitrogen requirements from past research. So if I'm 10 years past when the research was conducted, that's really the only data I have, really, right, to determine a recommendation. But since yield's increasing so quickly, they can quickly become inaccurate. And so if I had the recommended nitrogen supply right here on this particular axis over time, and I have all the different points right here where research was conducted, right, and the appropriate nitrogen requirement factor was determined, we can see that if I were to use the 8 pounds of nitrogen per ton every year using average annual yield increases, I'm soon going to be having an increase in the amount of nitrogen that's being required. And it could potentially become fairly high compared to potentially a range where it's needed to be at, right? You can see that when research was conducted at this point in time, the recommended nitrogen really dropped way down from that research that was conducted by the University of Idaho. So this whole period of time right here, from here to here, I'm oversupplying nitrogen by a considerable amount, particularly as I get farther and farther along in time. But I recalibrate the system. Now I'm back here again. But now I haven't conducted any research from 1997 to 2011. So if I apply this factor with the yields over time, this is what ends up happening to my nitrogen requirement. It drastically increases to a point where I could potentially be way oversupplying nitrogen compared to what actually is needed. And then when the research is conducted in the early 2000s, the data shows, oh, I should be way down here. This is where I should have been. So this whole time here, I can potentially oversupplying nitrogen outside of a range that needs to be in, that's optimum. And again, the same thing has happened, right? Since 2011, if I continue to use this factor of 5.5, I'm drastically increasing the amount of nitrogen I need to supply that may be excessive because yields are going up, until new research is conducted in 2018, 2019 that says, no, I need to be down here at about 4.3. So utilizing this nitrogen requirement factor leads to this potential scenario that at particular points in time, you can be way oversupplying nitrogen relative to what actually is needed. This graph shows the amount of excess nitrogen fertilizer that would have been applied utilizing a nitrogen requirement yield goal based approach versus what was actually needed to grow and maximize the sucrose yield at each of these research sites. So we have the 2005-2010 data set from each site year from that study, and we utilize a nitrogen rate factor of 7 for that. We also, in 2018, 2019, those 6 site years, we use a nitrogen requirement factor of 5.5, which is valid during that period of time. And you can see that utilizing the yield goal based approach with the actual yields that we got in that in those studies, that we would have been applying excessive fertilizer for most of the study sites. There's only a couple study sites, as you can see, that would have been close to about the same. But the average excess nitrogen fertilizer applied in 2005-2010 was about 90 pounds of nitrogen per acre, and that was about 71 pounds of nitrogen per acre in the 2018 and 2019 data set. So in summary, the current data, the historic data, all suggest that the static end range approach would be appropriate in the past, it's appropriate now, it's valid now, and will likely be valid in the future. The question then arises, will these ranges change over time? Well, this can be evaluated with continued evaluation studies over time to assess whether or not these need to be adjusted. It's also important to understand there's a lot of variability within these studies in terms of what nitrogen supply was needed to maximize yields. I think that each producer is going to need to really understand what their range is. And that's why we call it a static nitrogen range approach, not a static nitrogen approach, because we believe that different areas, different soil types, different microclimates, the actual amount of nitrogen needed to maximize sucrose yield may vary a little bit. And so it's up to the producer and consultants to really maybe understand the system at that particular location to evaluate that. Currently, Amalgamated is conducting static range nitrogen verification plot studies over the next year. I believe this coming year is the last year for that, just to see, make sure this is still playing out in different areas and different types of conditions. With that, I want to say thank you. Here's my information. If you want to contact me, my email address, phone number, please, if you have any questions, please just don't hesitate to call me and we can talk about any of this.